All right, so we are now going to move into section 9.2 partial derivatives. So we just talked about our functions of several variables, which we need in order to do partial derivatives here. So the easiest way to explain partial derivatives is to think about it like this. Whichever variable we are taking the derivative with respect to, everything else is a constant. So you can think about it as everything else as a number. In other words, we have no product rules of X and Y or Y and Z in this case and everything. Notice there is a slight difference in our notation for each one of these. Yes, I know in class, like I've told y'all before, I normally write script D's as my derivatives, but understand that a normal derivative, so normally we have dx. Notice over here we have script. So the script tells us that we're going to use a partial derivative. So what we have here, in order to find the partial derivative of our function w with respect to x, so if w was equal to x squared minus xy plus y squared plus 2yz plus 2z squared plus z. Yes, that's a lot of different style terms in there. But the only ones that I care about for this case, for partial with respect to x, is I care about these pieces only. W equals x squared minus xy, because those are the only ones that have an x involved in it. So the partial of w with respect to x is dw dx. The derivative with respect to x of x squared gives us 2x. The partial derivative with respect to minus xy, y is just like a number. So a number times x would just give us the number. So that's when we have 2x minus y as our partial derivative with respect to x. If we wanted to find this same thing with respect to y, the only terms that we care about are these middle three terms. They're the only ones that have our y variable in it. So when we go with partial of w with respect to y, the partial respect to minus xy is minus x. Partial of y squared is plus 2y. Partial of 2yz gives us just 2z. Now, if we were talking about the partial with respect to z, the only terms that we care about are those circled terms there. So the partial with respect to z of 2yz is going to be 2y. Partial of 2z squared is 4z. Partial of z is just 1. So we're literally just taking the derivative with respect to whatever variable is given there. Now, some other type of notation that we could have is this little notation here. F sub x, f sub y. This notation here pretty much tells us this is our function f, its derivative with respect to x. We looked at this notation a while back. We just haven't really used it a lot because of only having one variable. Now that we have multiple variables, this is the easiest kind of way to kind of look at this. I prefer this type of notation, f sub x, f sub y. So if we're looking at f of xy equals 3x squared y plus xy, we want to find the partial derivative with respect to x only. So both terms have x and y in each case. So 2 times 3 gives us 6xy. Don't forget that y as a multiplier because it still is a constant over there. Plus the derivative of xy with respect to x is just y. So y is a constant, got to treat it that way. If we wanted to do f sub y, now x is a constant and x squared is a constant. So the derivative of 3x squared y with respect to y is just 3x squared. The derivative of xy with respect to y is just x. So our partial there would be 3x squared plus x. We can have more complicated functions. It doesn't matter what we're looking at, we can still have it. We got to be careful in terms of product rules or variations here. So we have f of xy equals e to the xy plus y ln x. Again, finding the partial of x and the partial of y. So the partial with respect to x, so we take the derivative of that exponent of e with respect to x is just going to be y times my original exponent of e to the xy plus y is a constant in the second case, so y times the derivative of ln of x is 1 over x. So if we simplify that, we get y e to the xy plus y over x. Likewise, we can do the same exact thing with respect to y. When we do it with respect to y, we're going to get x. The derivative of xy with respect to y is just x. So x times our e function of e raised to the xy. Plus, in the second case, ln x is our constant. So the derivative of y is just 1 times ln x. So simplifying, we get x e to the xy plus ln x. Don't get confused on whatever derivative we're looking at. Always key in on whatever this subscript is here. The subscripts tell us what derivative we're taking it with respect to in each case. So, an application for our business and everything. So a cellular phone company has the following production function for a certain product. P of xy equals 50x to the 2/3 y to the 1/3. Where P is the number of units produced with X units of labor and Y units of capital. We're told to find the following three things. Find the number of units produced with 125 units of labor and 64 units of capital. Then we're going to find the marginal productivities and then evaluate the marginal productivities at X equals 125 and Y equals 64. So for part A, we're literally going to plug in. We're just going to plug in X and Y and get an answer. For part B, we're going to find its derivative, find all the partial derivatives. Part C, we're going to evaluate both of our partial derivatives at 125 and 64. So by simply plugging in 125 into our function, 50 times 125 to the 2/3 times 64 to the 1/3. Well, 125, the cube root of 125 is 5. 5 squared is 25. That's how we get to 25. Could also just type it in your calculator, 125 raised to parentheses 2 divided by 3 in your parentheses. So if you were to type this into your calculator, it would look something like this, which will give you the 25. 64 raised to the 1/3, you could do it the same way, and you would get 4. So 50 times 25 times 4 would give us 5,000 units. So the marginal productivity of labor is going to be our partial derivative with respect to X, because that's our production. So by taking the derivative of 50x to the 2/3 y to the 1/3, we're going to leave y as a constant. So therefore 50 times 2/3 x to the negative 1/3 times our y to the 1/3. If we simplify that, 50 times 2 gives us the 100. We got a 3 in our denominator. We can take that x to the negative 1/3 and put it down. So it could be 100 over 100 y to the 1/3 over 3x to the 1/3. If you wanted to, you could also write this as 100 over 3 times x divided by y to the 1/3. May gain something out of that, may not. It depends on what we're trying to plug in. If we were to find the marginal productivity of capital now we're going to do it the other way. We're going to find the partial with respect to y. So by finding the partial with respect to y, that's 50 times 1/3 x to the 2/3 y to the negative 2/3, which would simplify to 50 x to the 2/3 over 3 y to the 2/3. Again, we could write this as 50 over 3 times x divided by y, all raised to the 2/3. Just depends on what we're going to do in the next step if we want to do this or not. In other words, this x divided by y could simplify and make it easier if we do it that way. So for the marginal productivity of labor, and then therefore P sub x of 125,64. You plug in 64 for y, 125 for x. So 100 times 64 to the 1/3 over 3 times 125 to the 1/3. Cube root of 64 is 4. Cube root of 125 is 5. So 100 times 4 over 3 times 5. If we reduce that, we would get 80 over 3, which is approximately $26.67. We could do the same thing for the marginal productivity of capital. So we literally are just plugging in to our derivative of P sub y. So 50 times 125 to the 2/3 over 3 times 64 to the 2/3. So 50 times 25 divided by 3 times 16 gives us 625 over 24. You could have also just multiplied this out and divided here. So 50 times 25 divided by the 16 times 3, you would have got to the same exact answer. Now, just like before, we can have second order or higher order partial derivatives. So by doing that, d2z over dx dx means the second derivative of our function f over dx dx, or d2z over dx squared is d2f over dx squared, which is the same as fxx. So all this is really telling us is take the partial with respect to x and then take the partial with respect to x again is what this means. We always work left to right. So in the second case, d2z over dy dx equals d2f over dy dx, which is the same as f sub x, then y. So if you're reading the little short notation there of f sub xy, we go left to right. So left to right. If we are here, we go right to left. So we got to kind of pay attention on which notation. I like the F notation better because it's just like you're reading a book. You read left to right here in America. So as long as we're doing that, we're good. That's the way I like to see it. We can also have d2z of dx dy equals d2f over dx dy, which is f sub yx. Take the partial with respect to y, then with respect to x. The last second order derivative we could have is d2z over dy dy, which is d2f over dy dy, which is equal to d2z over dy squared, which is equal to d2f over dy squared, which is equal to f sub yy. Now, one thing to note, when we start talking about these squared variables here, down here, this is not a power. Do not square your variables. This is just saying we're taking the derivative of that variable twice. So For this example here, we're asked to find the second order partial derivatives for all four possibilities. So the first case that we would have in each one of these would be to take our first order partial derivatives. So we need f sub x and f sub y. So f sub x would be 2xy cubed plus 4x cubed y plus e to the y. F sub y would be 3x squared y squared plus x to the fourth plus x e to the y. So notice what's in these parentheses in both of these cases is our f sub x. Because of our notation, we already took it in the first case here. In each case, we have to take our first order partial in order to get to the second order partial. We cannot just jump to the second order partial there. So once we do that, since we're finding f sub x in this first case, we take our first partial derivative and we take its derivative again with respect to x. So we get 2y cubed plus 12x squared y. The derivative e to the y is 0, so it disappears. For f sub xy in the second case here, we already took it with respect to x. Now we need to take it with respect to y. So that will give us 6xy squared plus 4x cubed plus e to the y. Going to our second order with respect to y first. So again, I'll refresh us that f sub y is 3x squared y squared plus x to the fourth plus x e to the y. That's exactly what we have in our parentheses because that's the first thing that we are doing in each case. Now for the first one on this screen, now we got to take that with respect to x. So we get 6xy squared plus 4x cubed plus e to the y. For fyy, we get 3x squared y, or we get taking the derivative with respect to y of our f sub y. So we get 6x squared y plus x e to the y. The derivative of x to the fourth is a constant, so it's 0. So therefore, that would be our two things. Now, one thing to always note, f sub xy better always equal f sub y x. In other words, order will not matter whether you do y first, then x, or x, then y when we're taking these partial derivatives. This is kind of one of our checks to make sure that our derivatives are correct. This will tell us if our first order of x or first order of y is correct compared to what we're looking at.